Bismillahirrahmanirrahim. We begin with fragmentation. Why do we need this concept? Why do we need to fragment a packet? If you remember, when we did our MAC frame for Ethernet, we had spoken about different sizes. Okay? We had spoken about different sizes of the MAC frame. So for example, you have Ethernet, which can accommodate a maximum size of 1500 bytes. Similarly, you have different technologies. Okay, you have different communication technologies that will accommodate different packet sizes. So PPP is only 296, X25, 576. Whereas hyperchannel, you can actually have the whole packet as it is. You could have the maximum size of an IP packet and you could send it without the whole size. Okay? So why do we need the fragmentation? If you look at this diagram here, you have the source and you have the destination. Okay? The source and the destination are separated from each other by certain distances, and you have so many different technologies that the packet, if it starts from the source to reach the destination, it will have to go through so many different networks before it reaches the destination. Every network technology has got its own maximum size. Okay? It has its own maximum size for a packet. If you have a packet, a large packet, coming to a router of a technology that does not accommodate this, the size, this packet will have to be chopped into smaller packets, fragments. And then when they come out in here, they will be the size that the network can accommodate. So when they go to the destination, they will all be joined together to form the original packet. So for example, in here, we are beginning with our Wi-Fi, right? We begin with Wi-Fi. The packet goes to the access point, and here you have your normal LAN, okay? The 10 Mbps Ethernet LAN. Now, let's say the packet is fine until here, okay? And let's say the size of the packet is 1400 bytes, okay? This is the size of the packet. If on this way, if the packet, so you see here is going through fiber optic, gigabit Ethernet, and then a 10 Mbps Ethernet down to the destination. If in this route it encounters a network whose maximum transmission unit size is less than this, the packet will have to be chopped. So for example, if you look at this table, if we are going from Ethernet, okay, if we are going from Ethernet to a PPP network, And if the packet size was 1400, PPP, what's the maximum size? 296. So it cannot accommodate 1400. So this 1400 sized packet will have to be chopped, okay, fragmented into sizes less than 296, okay, sizes less than 296. And then each fragment will become a separate IP datagram and be transmitted over the PPP network. Right? So this is what happens. A packet can be fragmented anywhere in the network. Anywhere it can go, it can be fragmented. However, it can only be joined to make the original packet or datagram at the destination. Only the destination can join the fragments together. You can chop them anywhere in the network, but you can only join them at the destination. So now let's look at how this fragmentation takes place. We're looking now at the different fields, the flags. Remember the flags field we saw in the IP header? Now we're looking at the meanings of these fields. You have the first bit in the flags field reserved, so you don't use it. And then you have the D bit. This means do not fragment. If this bit is set to 1 in the packet, it means don't chop this packet. Don't fragment this packet. So what happens if now we are reaching a network whose MTU, maximum transmission unit size, is less than the packet size? What happens in this case? If the D bit is set, and if the packet is too big for the new network, it will simply discard the packet. It will discard the packet and will send an ICMP error message to the source saying the packet could not go. So this is the function of the D bit. Next we have the M bit, more bit. Okay, the M bit will tell you if this is set to 1, then the M bit will tell you there are more fragments. So if the M bit is set to 1, it means that this fragment is not the last fragment. There are more fragments after this. If the M bit is 0, okay, if the M bit is 0, it can mean two things. It can mean there are no fragments, so this is the only packet or fragment, or this is the last fragment. There are no more fragments after this fragment. Okay, so you have the D bit and the M bit, two very important bits. Based on these bits, we will know what to do, where the packet belongs to. Now let's look at an example of fragmentation. Let's say we have a packet. Okay. It doesn't seem to like to draw it. Let's say we have the packet. Okay. Now in this example, what's the size of this main packet? 4,000 bytes. Okay, it is 4,000 bytes. And remember, the packet will begin at 0. Okay, oh, what's happening here. The packet begins at 0. And we said the total size of the packet is 4,000 bytes, right? This is the data, remember. The data is 4,000 bytes. So because we are starting at 0, we end at 3999. Okay, the original packet. Now, this packet is going through Ethernet. Okay? And the maximum size that we can tolerate in here is 1500. Okay? That's the maximum size of the whole packet. Header plus data, remember. Header plus data should be not more than 1500 bytes. Okay? So the maximum length for this network is 1500, including header. Now, what we do in here is we are dividing the packet into 3 parts. We are fragmenting it into 3 parts. Okay, and we are taking 1400 as the standard size. Remember, this is not the only number you can take. You could take more than 1400. You could take less than 1400. Okay, it does not matter as long as you are less than the maximum fragment size. But for this example, we have taken the standard length of the fragment to be 1400. Okay, so we have now, we will have the first and the second packet of 1400 bytes. Okay, and we have the third packet as 1200 bytes. Okay, it doesn't matter. We are below the maximum length. Remember, this is the data we are dividing. Okay. Now, one thing you have to understand is that this number that you choose for the packet, it must be divisible by 8. Okay? It has to be divisible by 8. You have to get a multiple of 8. Why is that? Because if you look at the IP header, the fragmentation offset field is only 13 bits. So it may not be able to accommodate, it doesn't have enough bits sometimes to accommodate the entire length of the packet. Okay, so we will have to divide. So the maximum number that we are taking for the fragment, it should be, or the size of the packet fragment should be a multiple of 8. This is very important. Okay, you can't just take any number. So now, in this scenario, we have the first fragment 0, because this is 1400 bytes in size, it is from 0, 1399. Okay, and then it will start at 1400 byte. Okay, byte number 1400, and it will go all the way to 2799. 2.99. Okay? And then the third fragment will begin at 2800. So in this way, we have divided a big data payload packet into smaller fragments. What can you say about this number? If you look at this number, 1400, this one will actually give you the length of the previous fragment. 2800, it's giving you the length of the first two fragments. Okay, this is very interesting. Now, what do you do about this number? You take this number and you divide it by 8. Okay, so this is giving you 175 and 350 respectively. Okay, so you have 175 and you have 350. This is what you have. Okay, what does this mean? This is your offset. Okay, this is your offset. This will go in your offset field in here, fragmentation offset. Okay, it will go here. Based on this value, you can say many things about the fragment. You can tell many things. For example, in here, what is the offset? It is 0. When the offset is 0, you know this is the first fragment. Why do you need this offset? It's very important because this will tell you where the fragment is with respect to the original 0. It will tell you where it is. So at the destination, okay, at the destination, if we have the packet now coming in, okay, let's say this packet comes in first, fragment 3 comes first, okay, so now we have the empty space, let's say, for the whole packet at the destination. You're having this fragment coming first. What do you do at the destination to this fragment? You look at the offset and you multiply it with 8. So you have 350. So at the destination, you are taking 350 times 8. And this will give you back the original value, the original offset value, which is 2800. So now you know exactly where this packet sits. Okay, the more bit for this fragment will be 0 because it is the last fragment. So now you know that, this is my last fragment. So you know that this packet will fit in here. And then let's say you have the second fragment that comes in is the first one. When you look at the offset, which is 0, you know immediately that this is the first packet, and then the source can place it in here. And then when you get the second one, it fits in here. So it does not matter who comes first, because we know the exact value of the offset with respect to the original 0, we can easily place the packet in its respective place. Okay, and remember, when you get the packet at the destination, you take the offset value and you multiply it with 8. At the source, or when the packet is getting fragmented, you divide the offset by 8, and at the destination you multiply it with 8. Okay, so this is what's happening in fragmentation. So you're having a big 4,000 byte packet being divided into different fragments. Now, let's look at this scenario. This is a very interesting scenario. We have done this in class already, but this is a good recap for you. So we say in here, this example will actually show you exactly how fragmentation works. At this source, you're having the original packet. This is the original datagram, okay? IP packet. Pay attention to the fields. At this point, the packet has not been fragmented. It is in its original size. Okay, before it goes out, it is in its original size. Here, the header length field is 5, which means the actual length of the header is, okay, so header length is 5 times 4, which is 20 bytes. 20 bytes is the header length. 4020. This is the size of your datagram. And see here, you have 4,000 for the data and 20 for the header. Okay, that's why it is 4020. This is the ID, 14567. Okay, this is the ID. And as you can see here in the other, all the fragments have got the same ID. Okay, so this will tell the destination that they all belong to the same original IP, same original packet. Okay, datagram. In the original packet, the more bit is 0, which means this is the only datagram. There are no other fragments. And the offset is 0, right? So when you're looking at more bits 0 and the offset 0, it means this is the only packet. Okay? So based on these two fields, you can tell a lot about the packet itself. Now, at this source, this packet is getting chopped into 3 fragments, F1, F2, and F3. Okay, it's getting chopped into 3 fragments, as we saw in the example here. Okay, it's getting chopped into 3 fragments. The same thing is happening in this scenario. So we have the first fragment 1400, second fragment 1400, third fragment 1200. You have 1420, which is header plus data. So the data is 1400 and plus 20 for the header, and you get 1420. All the fragments will have the same header length as the original packet. Now look in here. This is the first fragment. The offset is 0 and the more bit is set to 1. This means it's the first fragment and there are more fragments to come. Second fragment, we said the offset was 175. So there you go here. As you can see, you have 175 in the offset. The more bit is again set to 1, which means this is not the last fragment. There is still more fragments to come. Okay, and again 1420 is the total size of the datagram. Now look at this third packet. Third fragment. Offset is 350 and the more bit is set to 0, which means This is the last fragment with respect to the original packet or datagram. Anytime we do any fragmentation, it will always be with respect to the original datagram. Now, so we have this scenario. So F1, F2, and F3 are the three fragments. F1 and F3 take this route and they reach the destination, but F2 goes a different way. And F2 in here, it's getting fragmented again. So you have F2.1 and F2.2, okay? And then eventually all fragments reach the destination. Now look at what's happening here. F2 is getting fragmented into two more packets. We're saying the size is 800 and 600, okay? So if this is F2, fragment, okay? This is the F2 fragment, and we are saying it's getting divided into 800 and 600. Now, pay attention carefully. It's starting at 1400, right? And it's going to go all the way up to 1400 plus 800 minus 1. So this will be 2199. The next will start at 2200 and it is reaching 2799. Again, remember this number has to be divisible by 8. So now what is the offset for this packet? We have 800 divided by 8 and 600 divided by 8. Okay, so this will be your offset fields. I'm sorry, you have 1400. You have to take offset based on the first byte. Okay, so you have 1400 divided by 8, which is 175, and you have 2200 divided by 8, okay, which is, how much is that? 275, okay, 275. So these are your offset. So remember, your offset will always be your first byte divided by 8. Okay, now these values are entered in these two packets. Okay, so you have 820 is the total length, data plus header. Identifiers are the same. The more bit is set to 1 in both packets, remember. Okay, so you have offset 175, offset 275. Here, why is the more bit not 0? Because, is this the last packet with respect to the original datagram? No, it isn't. The original packet, the last packet or the last fragment is F3. So this is why in here your more bit will still be 1 because it will say, I am not the last fragment, there is another fragment coming after me. Okay, so this is how the fragmentation mechanism works in IP. Now, quickly looking at some examples, it says a packet has arrived with an mbit of 0. Is this the first, the last, or the middle fragment? If the mbit is 0, it means there are no more fragments coming, okay? But we don't have the offset value in here. If the offset is 0, then we will know this is the first, but we don't know the offset. So this could be the first, I'm sorry, if this is 0, this could be, there could be two options in here. One, it is the only packet, or the second one, it is the last fragment. Okay, you could have two options in here. The packet has arrived with an m-bit value of 1, which means there's more fragments coming in. Is this the first, last, or middle fragment? So if this is 1, it means there is at least one more fragment coming. So this means it could be the first one or the middle one, but it is definitely not the last one. Okay? A packet arrives with an m-bit value of 1 and an offset value of 0. Is this the first, last, or middle? So we know m is 1, and more bit is 1, more fragments coming, but the offset is 0, which means it is the first fragment, because the offset value tells you that. Packet arrives in which the offset value is 100. Okay? What is the number of the first byte? Do we know the number of the last byte? And how did we say we know we can calculate the first byte in a fragment? We say we take the offset and we multiply it with 8, right? At the destination. Remember, at the source, you are dividing it. At the destination, you are multiplying it with 8. So you're taking the offset value, multiplying it with 8. This gives you 800. So the first byte in this packet is 800. But do we know the last? No, we don't know that. We need more information. Packet has arrived in which the offset value is 100. Again, it means it is beginning at 100 into 8, which is 800. Okay? The value of the header length is 5, and the value of the total length is 100. And again, we said if the header length is 5, it means 5 times 4, which is 20. And the total length field is 100, which means header plus data, all this thing is 100. Okay? We know header is 20, which means data is 80. So if the data is 80, which means now we can know where this packet ends. It will end at 879. Okay? So the first byte is 800 and the last byte is 879. So this was fragmentation. In the next video, we will look at ICMP.